Hi everyone, I'm excited to present our paper titled Leveraging Temporal Images for Biomedical Radiology Analysis, aka Libra. This work was done in collaboration with my three advisors, Zaichao, Jack, and Adam. The main idea behind the Libra is to enhance the ability of multimodal large language models to process temporal paired chase X-ray, particularly for the task of the radiology report generation. Let me show you some background to help you better understand the task. As shown here, a typically multimodal LLMs takes an images as input along with the instruction prompt that asks a question related to the image. Then the model generates a response. On the language side, rely on the LLM. It handles the decoding and generation of the final answer. But there is the key challenges. LLM by default cannot process any other than task. The tokenizer is designed only for the task. That is why we need an additional module that can embed it as other modalities like images into the format that neural networks can handle. This work explores how to apply this kind of multimodal LLM framework to the radiology domain, especially for the chase X-ray analysis. The setup is very simple. The input is the chase X-ray, and the output is generate a response based on a given prompt. That typically involves two types of the task. The first, visual question answering. Another one is report generation, where the model produces detailed medical report rather than just a short answer. This task is the main focus of this work. Let's talk about more detail on the report generation. It's pretty straightforward. The model takes a case X-ray or paired of the X-ray and generates a report that mimics when a radiologist writes the report. Now here is the key issue. Most existing models only look at the single image, which means they completely ignore the temporal dimension, whether disease is getting better, worse, or staying the same. So what is a temporal hallucination? Here are the two examples. Single images case, the model generates incorrect content. The phrase, like in comparison with prior blah blah blah, is completely wrong because there is no prior image. So the model make mistake refers to the non-exist prior studies. Another one is the temporal images case. Now we actually have the prior image, but the model misinterprets the temporal changes. The model states the patient is unchanged, but in reality, the ground truth report is the totally opposite. This type of the error can be dangerous in the clinical setting, and fix this issue is what Libra aims to do. And why does it happen? The main reason is the dataset bias. In the clinical practice, radiology always compare paired images when writing the reports. So naturally, the report often contain comparative phrases like compared to. This means that temporal information always remains embedded in the original report. So how can we handle this? One common approach is to paraphrase the training reports using tools like ChatGPT to remove temporal reference before training, but this forces the model to ignore temporal information entirely. Another approach is to treat multi-image cases as a multi-turn conversation, where the prior and the current images are processed like the dialogue history. At each turn, the model focuses on answering questions about the single images and then summarize. This may sound reasonable, but it relies heavily on the LLM's ability to distinguish between two images and reason over the temporal relationship. To address this, we propose a new framework that indicate the model to learn paired image features, allowing the model to fully utilize temporal information rather than ignoring or misinterpreting it. Instead of relying on prompts or sequential token, which only operate a shadow layer, our method introduced temporal modeling directly into the architecture, embedding this reasoning into the model's hidden space. Here is the overall architecture of the Libra. You will notice that it follows a classical structure, a visual encoder, a connector, and LLM, choosing the right pre-trained model is crucial for performance, especially we use the Radiology as a frozen biomedical image encoder, Mediton, a biomedical LLM, both of them trained on specialized medical tasks. In ablation study, we confirmed that incorporating domain-specific prior knowledge can boost the model performance. About the connector, Libra used a hyperstructure that combined the convolutional neural network and transformer blocks, allowing it to process and align temporal features between paired scans. One challenge in the real-world setting is that not every scan has a prior study available. To ensure consistency between training and inference, we introduced a simple but efficient solution. A dummy prior images, which is just a copy of the current images. This helps mitigate suspicious reference to non-existing scan and will maintain a consistent input for the model. Why does it matter? By modeling the temporal relationship at the architecture level, Libra is closer to a real-world clinical sensor. For example, if a doctor says that a patient's condition remains stable, this means the current scan and the prior scan are nearly identical, which align with our temporal modeling approach. Now let's talk about the most important part, the connector. It consists of the two key components. One is the layer feature extractor, another one is the temporal fusion module. The goal of the extractor is to aggregate a multi-layer feature from the image encoder. Now you may be wondering why use all hidden layer instead of just a single one. Well, most models like lava typically only use the last or plutonium layer of the image encoder for global features. Actually, it will lose some information in the shadow layer. However, in Libra, we utilize all hidden layers. This helps us capture the richer multi-scale representations. This gives a more fun gradient feature of the all hidden layers. And pass to the temporal fusion model. Now we need to combine the current and prior image representations. It treats the prior images as an auxiliary modality and apply an attention-based mechanism to integrate it with the current image. This ensures that the model understands the temporal difference instead of just concatenate images in the latent space. So the current image is always being the main query in the transformer blocks. Finally, MLP is used to align feature dimension with the language model space. For training, Libra follows the classical two-stage pipeline, which is widely used in the multi-modal LLMs. In the first stage, we only train the connector. We'll keep the visual encoder and LLMs frozen. The goal here is to align the image feature with the text space. In the second stage, we fine-tuning on the specific task, report generation, and add a LoRa to the LLMs, keep all frozen to make sure the model's following instruction ability. Now let's see the performance. Overall, our results are strong across most evaluation metrics, especially when compared to other similar-sized model. It is important to notice that other models in comparison use the full fine-tuning in their second stage, but we only use the LoRa. Finally, our model is ranked top 3 on the latest open source leaderboard for report generation on hidden dataset for fairness, verified by the third-party Harvard Medical School. Here is an interesting cases corresponding to the temporal hallucination type I mentioned before. A single image inference, the model generates a report based on only on the current images without additional useless information. If we provide prior images, the report will incorporate the temporal phase, like as compared to blah blah blah, simulating how the radiologists compare scans to write the radiology report. And the most interesting is if we swap the current and prior images, the model reverses its findings, like the worsening become improving, just to show the model can understand the direction temporal changes rather than memorize the pattern of the input. and thanks for your listening.